All right, so let's take a gander here. Again, I meant to say the isosceles, excuse me, let's try that again. I meant to say the horizontal, so looking like this. So now I'm going to mark it. And notice that I could actually mark it with all singles. Why? And this was, I meant to also put that the whole thing is an isosceles triangle. Okay, so as we focus on it, we clearly see that the top is not just a triangle, the top is still an isosceles triangle. And more specifically, what's true about the bottom shape? It is what type of? It is a trapezoid. Does anybody know the name of that trapezoid? It's also an isosceles trapezoid. So we'll define that later, or we'll formally define it later. But it just means that it has a pair of congruent legs. All right, so now let's start to think about what's true about the interior angles? Here, 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 and here. We know that all the angles sum to 360. Now that's true only because it's a quadrilateral. So that's not super special, but it is something to know. So the second thing we know is we certainly know that this angle and this angle are supplementary, and this angle and this angle are supplementary, but not consecutive this way and not consecutive this way. So that one's hard to say. But what we could say is something like this, where we say two pairs of consecutive angles are supplementary. Good, and that's because parallel lines cut by a transversal, consecutive interior angles are congruent. All right, we can also say that opposite angles are supplementary. Good. And there's one more that we could probably see. Yes. If we consider the entire shape, the isosceles triangle, we know that these angles down here have to be congruent in the triangle. Well, if we cut the top of the triangle off, that doesn't change the fact that these are still congruent. And if these are congruent, then these have to be congruent up here because of supplementaryage. So, what do we call those? We can't necessarily say top and bottom because it could be shifted like this. So, in the end, those have special names. They're called base angles. And so we could say that base angles of an isosceles triangle, trapezoid, are congruent, or each pair. Each pair of base angles of an isosceles trapezoid are congruent. We will be chatting about two things. We're going to verify, which that's partially a verification there, and we're going to use properties of our friends trapezoids and kites. So let's walk through some definitions here together. What have we? So it is a quadrilateral with one pair of parallel sides. You could be more specific and say one pair of opposite sides are parallel. But this is kind of it, that's implied. Before we can officially define isosceles trapezoid, we probably should draw one so that we know what we're talking about. This here, the parallel sides are called the base. Each one of them is called the base, which means the non-parallel sides are called the legs. So in defining an isosceles trapezoid, we would say this. Trapezoid with congruent legs. No big deal. Now again, this diagram actually applies to both both terms here, over here. More specifically, when you did draw this out, we would mark the congruences there and the parallels there. If we were to draw a kite would look something like this, and we tend to draw it in this upright fashion, but it doesn't have to be that way, where we have a pair congruent there, and a pair of sides congruent there. So we've got congruence here, congruence here, congruence here, congruence here, but opposite can't be congruent, because if opposites were congruent, we would end up being rhombusification. Notice this is a quadrilateral, and some people might even argue that if you wanted to name that type of quadrilateral, it's actually a trapezium, meaning no parallel sides at all. There are no parallel sides in a trapezium. And the last thing is about any trapezoid. So I'm going to draw a common trapezoid like so. And a mid-segment is exactly what you think. It's the midpoint of the legs to the midpoint of the other leg, such that we have congruence there and a congruence there. And the segment that joins the midpoints of the legs, right there. All right, so let's take a gander and let's officially state that. The midsegment of a trapezoid is A, parallel to the bases, and B is 1/2 the length of the sum of the bases. And another way to put that is to say average. So to mark this up, we know that we have parallels there. And if this base length was A and this base length was B, then this one is going to be A plus B divided by 2. So here, if we're going to find out what the length of the midsegment, whose name is xy, we would say that the length xy here is going to be 1/2 of the 16 plus the 8. Or just add them and divide it by 2. So in the end here, we get 12, of course, which makes sense. Why? Because we can count 8, 12, 16. Add 4, add 4. So that pattern works pretty well. Add 4, add 4. So we know that it works. Oh, now to set this one up, there are 2 ways to set it up. Remember that this one is equal to the 2 bases added together and divided by 2. Another way to say it is this. Twice the midsegment is going to equal the sum of the bases. So that might be a little bit easier to set up, only because we're not dealing with fractions as much. Now, of course, to answer this question, we have to combine like terms. Our ultimate answer is going to be TU equals something. All right, so we're going to look at 2 properties. Remember, trickle-down economics here, that every single property of an isosceles triangle also includes the properties of the trapezoids, therefore includes all the properties of a quadrilateral. So that all trickles down. So it's everything that we've talked about trapezoids before and plus tax. So here, the diagonals of an isosceles trapezoid are, any guesses? Congruent. Word to your grandmother, which means that RP, segment RP, is going to be congruent to segment TA. Ta-ta for now. And then next, each pair of base angles. So we define base angles. So this is a base right here. So angle T and angle P are base angles. And RA is a base, so that means angle R and angle A are base angles, and they're congruent. Notice what we're not saying. We're not saying a base angle from here and a base angle from here are congruent. If that were the case, this would end up being a not trapezoid. It would end up being probably a parallelogram. So, and more specifically, it would end up being a rectangle if those were congruent, and if these were congruent, it would be a parallelogram. So the answer here, base angles of a trapezoid are also congruent. Paying attention to angle R, congruent to angle A, and then angle T being congruent to angle P. Got to be aware of how orientation is. Don't just say the tops are congruent to each other, the bottoms, because again, if it's rotated this way, then we end up getting these 2 here and these 2 here. So we have to pay attention. The bases are parallel. The bases are parallel. B1 and B2 are parallel. And that's essentially true for other shapes. As we set it up, and if it asks for a reason, always be prepared to give a reason, is we could say something like this, that the measure of angle A plus the measure of angle D is equal to 180, And the reason for that is parallel lines cut by transversal consecutive interior angles are congruent. Angles are congruent. So quickly we can solve that. The measure of angle A is going to be some great value, 125 degrees. Next, therefore, we know that the measure of angle 2 has to be 125 also. And if you were asked for a reason on this one, you would say base angles of an isosceles trapezoid are congruent. And that would be the same reason for the measure of angle 3 being 55 degrees. Base angles of an isosceles trapezoid are congruent. All right, and the last two things we're going to look at before we look at a proof and summarize. Summarize our best friend's quadrilateral. If you were to sketch out the diagonals here, take a guess, take a hypothesis. Good. Diagonals of a kite are perpendicular. What other shape, what other quadrilateral has that same property? Anybody? Just call it out. A square does, and a rhombus. So a rhombus and a square is always going to fit. So this does work, but it doesn't mean, so notice the converse is not true. Just because the diagonals are perpendicular, it doesn't mean it has to be a kite, because it could be a square or it could be a rhombus. So we've got a couple options just because that's true. So that's why we don't do the converse for some of these. This one says, I start with a kite, I end with diagonals being perpendicular. All right, this one over here. So I did clarify that these two angles here, because they are where the congruences are, those guys are called the vertex angles. Just like we talked about the vertex angles of an isosceles triangle. So the vertex angles are where the congruences meet, which means that B and D are the non-vertex angles. So if we wanted to clarify this and say one pair of opposite angles, or we could say the non-vertex angles. And I should clarify of a kite. And in this case, the non-vertex angles, what would you hypothesize about angle D and angle B? They are going to be congruent. All right, so let's look at an example here. Since we know this is a kite, why do we know it's a kite? Because congruent, congruent, and these are congruent there. Which means this has to be 90 degrees right there. And we know that inside forms this triangle right here has to be a right triangle. Therefore, the two acute angles are complementary. So there's a couple different reasons to give. The big reason to find out what the measure of angle 3 is. The measure of angle 3 is equal to 39 degrees. And the reason for that is because acute angles of a right triangle are complementary. All right, of course, how did we know it was a right angle right there? You could have also given that information there. All right, we're going to use two ideas here. Number one, we know that since we have a quadrilateral, we know that all four sides are going to sum to 360 degrees. And we also know that the non-vertex angles of a kite are congruent. So if I just call this x, those are both x. So when I set it up using the 360, I can say 2x plus the 87 plus the 59 is equal to not 180. See if that one will erase. Oh, look, it erased. Is equal to 360. Now combine, etc., and solve to get. So that means the measure of angle 1 equals the measure of angle 2 equals 107 degrees. And of course, with your calculator, you can double check 107 plus 107 plus 87 plus 59 should be 360. We can also look here, just if you had to take a guess, it's a little bit bigger than 90. So 107 is a reasonable answer by the diagram, which isn't always to scale. The final thing that I will walk you through is a proof to this theorem. And this proof is going to be fairly straightforward. We're given that we have a kite, and our goal is to prove the theorem that says the non-vertex angles are congruent. Well, if I draw an auxiliary line, that is, a diagonal right here, notice I form two triangles. As we make a plan, why do the two triangles have to be congruent? Please. All right, so we do see that by side, 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 the triangles are going to be congruent. So I do have to write all the pieces down, and so let's write them out. Do the proof. Takes a while to do the proof, although we can quickly see that it's true. So this would be a formal version of the proof. Again, we state that it's a kite. We explicitly state side, 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 then the triangle's congruent, and CPCTC.